So I'm Conor here from Stony Brook University to present our work, improving user perceived load times using Gaze. So the info's right in the title, so let's just get into it. So what's the motivation for our work? Well, websites are exploding in number. There's over 966 million unique sites today as of 2015, and now there's over 1.1 billion. So as a result, performance is increasingly important for these sites. And Google is now using page speed as a major ranking factor in search. And Amazon reports for every 1 second decrease in page load time, or PLT, there's a $1.6 billion profit. So as a result of this, there's been a significant body of work from the network performance and web optimization communities in creating actually web optimization systems of which decrease page load time. There's been significant work from academia as well as industry, and many of these works have been featured at previous NSDI venues. So our work actually operates under the hypothesis that traditional page load time metrics, or traditional PLTs, used to measure the page load time do not actually correlate or relate to the user experience. So if this is true, then this leaves the effect on existing web optimizations which optimize the PLT, it leaves their effect on the user quality of experience uncertain. So in order to gain some intuitive examples as to why this might be the case in terms of PLTs, let's see how they operate on the modern web. So the first PLT of which we'll discuss is the window.onload metric. It's an event-based metric of which actually fires when all of the objects defined in the initial page load are fully downloaded by the network. So let's analyze how window.onload looks in terms of the page load performance on a few sites, starting with Amazon.com. So with Amazon.com, the onload suggests that the site loads at around the 8-second mark. And if we look at the visual rendering process of the page, it looks to be completely loaded. The user seems to look to be ready to interact with the site, ready to shop. However, if we move back to a much earlier similar frame at about the 1.5-second mark, we can see that all of the content in the client's initial viewport, all of the above-the-fold content, is actually completely loaded at this point. So the reason for this is Amazon does great work in actually optimizing their above-the-fold times. However, there's a lot of objects of which are bound to the onload, of which actually load a lot after when the user is likely ready to interact with the page, likely ready to shop. So onload can also underestimate the page load. If we move to gmail.com, we see that the onload fires at about the 1-second mark, likely way before the user is ready to interact with their mail, of which takes about 5 seconds to load. And the reason for this is Google uses a lot of dynamic client-side JavaScript in order to fetch a lot of web objects after the initial page load, of which aren't actually bound load to the onload metric. So we can see that there's a disconnect between when the user is ready to interact with the pages and when traditional PLT metrics, specifically the premiere of onload, is actually suggesting that the user is ready. Although we provided intuitive examples for the onload, we provide similar mismatches to other PLT metrics such as the speed index, which is a more visually oriented and newer metric, as well as some other systematic standards such as the DOM content loaded within the paper. So we've shown for an intuitive example, why users may be experiencing disconnects between traditional PLTs on the page. However, actually, how do we determine in the wild whether or not users are actually experiencing this disconnect? And for this reason, we actually introduce our own user-oriented, user-defined metric called the uPLT, or the user-perceived page load time, of which is defined via real user studies. So how do we actually obtain the uPLT? Well, we ask the crowd, when do you believe that the page is loaded? We then take to crowdsourced mediums as well as in-lab studies. We feature over 100 plus users, over 45 websites, representatively sampled from the Alexa Top 10K. And we ask these users, as the site is loading, when do you believe the site is loading? And they'll give their responses via input of a mouse click or a keyboard input. And finally, we formally define the uPLT as the actual median of these user study responses over 100 users. So just some actual specifics about the data itself. In order to establish consistency of this data, users may be experiencing different client-side networking conditions. Page loads are shown to have high variance. So we actually show users videos of the websites of which were taken from the actual websites loading in the wild. We also ensure quality of our measurements via two specific means. One is which we actually measure user reaction times, as there may be a disconnect between when users actually feel that the page is loaded and when they actually give this mouse input, and we subtract this out of all of our measurements. We also filter out erroneous responses, such as if users are just spamming input on a crowdsourcing medium in order to get paid as quick as possible. And we do that by monitoring pain events of the page. and using these to determine when the only possible possibilities of uPLT inputs will occur and filter out erroneous users. It also bears mentioning that there's a very related work, IORG, which was featured at Connect 16, of which utilizes a similar method to great success in order to obtain user-perceived page loads. And we utilize the success. We go off of the success by gaining confidence in our measurements as well. So let's actually, speaking of the results, let's actually go to the resulting measurements. So the first figure is just a simple box plot of the uPLT, the actual representing the spread over the 45 sites. So what we can see specifically is the narrow spread in the 25th to 75th percentiles of the box plot, about 3 seconds overall users. And what this means is there is a general consensus to this subjective question of when we ask the users, when do you feel that the page is best loaded? If we actually move towards comparing the uPLT to the traditional PLT metrics, specifically onload, we see that these intuitive examples are also being replicated in practice. So about 50% of the time, the onload is overestimating the median uPLT, which is, again, our definition of the uPLT. And about the other 50% of the time, the onload is underestimating the uPLT. And when it overestimates by an average of about 6 seconds, and similarly underestimates by about an average of a little over 2 seconds. So if we move to analyzing these results in aggregate, and what's even the trend of the uPLT relative to the traditional page load metrics, we see via the low correlation values that there really isn't a trend. And so there actually is a disconnect in practice between what the users are perceiving and what these traditional metrics suggest about the page being loaded. We also compare to the other metrics as mentioned before, such as the speed index, as well as DOM content loaded within the paper. And if you'd like to see analyses over binning these into different networking conditions, as well as across varying site categories, specific categories, you can consult the paper. So we've shown that there is a disconnect between the user quality of experience as well as traditional page load metrics. And going back to the earlier in the talk, we see that because there's actually a resulting disconnect between traditional optimization systems of which actually optimize for the PLT, as well as the user experience. So it remains uncertain about the impact of these optimization systems on the user experience. So let's see. So it's actually our goal in order to fill this gap to actually create a web optimization system of which specifically optimizes for uPLT. And our intuition is how we can do this is we should actually load objects sooner of which are important to the user. So if we prioritize these objects first, we can hence decrease the uPLT and improve the user experience. So the problem with this is identifying the relative importance of objects on the page is very subjective. Users are likely to know what they want, such as this example of MarketWatch.com. They're likely interested in the stock market information as well as the news, but likely not these obtrusive ads that show up on the page. However, there's no current way for clients and servers to actually know this information beforehand. And so the first challenge in creating such a system is how do we actually find objects of which are important to the user? And so for this, we actually choose to utilize gaze tracking or user eye gaze tracking on stream. And so this choice isn't out of the blue, as user eye gaze has been used to track user attention to high degrees of accuracy and consistency in the psychology and computer vision communities. And also there's been a great body of work and great effort from the computer science community in order to enable low-cost and personalized gaze tracking via webcam devices. So these webcams will actually find the locations of your pupil and actually automatically map them to locations on screen, which are shown to be highly correlated with the user attention. So how do we actually obtain the gaze data for the purposes of our study? Well, for that, we utilize real user studies, just like we did with the user-perceived page loads. We use a webcam-based tracker along with in-software-based solutions in order to obtain the actual locations on screen. We utilize 50-plus lab participants and the same 45 sites of which we already collected uPLT data for. And again, the goal of this is to actually find areas of specific web objects that are important to the user via their attention of gaze tracks. So in order to understand how we actually get this measure of attention, we need to understand a little bit about gaze itself. So human gaze consists of rapid left to right movements called saccades, interspersed with stability portions of the eye called fixations the coordinates of the fixations on screen, of which have been shown, are actually very highly correlated with the user's actual attention. So if we plot these fixations over the screen during the course of the page load, we can see the specific web objects, the specific areas of the page that a user may be interested in. However, if we plot these over multiple users, it seems that there's varying areas of attention and hence no real signal in terms of attention from gaze. However, if we overlay all of the fixations at once, we can see a definitive pattern in what the users are interested in during the page load. So fixations do overlap over all users. So it's from this intuition that we actually formally define our metric of which we obtain attention on objects, of which we actually utilize into a system for web optimization. And we call this metric the gaze collective fixation. So how it's actually calculated is we first divide the web page into its visual regions, of which are more respective of the web objects themselves. We then map the fixations of all users onto these visual regions. And finally, we estimate the collective fixation as the fraction of users who actually fixate on a given region. Now here for the example site of fcc.gov, we have we can see a few regions of high collective fixation, high user interest, of which are marked in green, as well as other areas relatively sparse of user interest, which are marked in red. So this was one specific example of how collective fixation looks, but does it produce a similar signal over all the sites in our corpus, over all the sites that we analyze gaze data for? And so in order to visualize this, we give the following CCDF of collective fixation, where the blue line actually represents the median case over all sites. So if we look at 2 points in this graph, we can see that about a quarter of regions have at most 0.3 collective fixation, and about a quarter of regions have at least 0.9 collective fixation. So what this really means is there are, when analyzed in bulk, objects with low user attention as well as objects with high user attention. So we're confident in actually using the collective fixation as a means over all sites to obtain areas of user attention. So now that we've seen how we can actually calculate the user attention, we actually go into the designing of a formal system of which uses gaze feedback in order to specifically improve uPLT by optimizing these regions of high collective fixation. And we call the system WebGaze. We envision the WebGaze architecture to be a collaboration between 4 entities, as well as have an offline and online component. So the offline component consists of web servers actually sending their site info to our WebGaze servers, of which will then actually redeliver the site to gaze providers, who will provide their valuable gaze feedback to the WebGaze servers to process the collective fixation. And from there, the collective fixation produce a high priority set of objects, of which it will send to web servers, of which will actually do the prioritization via the online component, of which actually utilizes the HTTP2 server push net mechanism to move from these set of high priority objects in order to deliver them as soon as possible to the user via the HTTP2 server push mechanism. So just some technical details about the prioritization process, the first of which is web page dependencies. So web page dependencies are a well-studied phenomenon in that web objects exhibit dependence on one another. And what this means in terms of a prioritization system is that if a user is very interested in a specific image, such as first.jpg, however, this is embedded in the DOM and actually rendered by a JavaScript, here shown as first.js, then it's unlikely to be useful to prioritize first.jpg without prioritizing its dependent script. So basically, WebGaze incorporates web page dependencies by using the wprof tool to do offline analysis of the web page in order to obtain not only the priority set of objects, but the dependencies for these objects to prioritize. The next technical detail is actually the mechanical aspect of the prioritization, which is HTTP2 server push. So server push actually works by actually allowing the server to piggyback objects on top of any given request from the client. So WebGaze actually utilizes server push by pushing objects corresponding to the region of high collective fixation directly with the HTML, so they're at the user side in the client as soon as possible. However, server push does come with the caveat that these resources in HTTP2 functions by actually allowing all of the objects to be downloaded in parallel, and so by pushing too many objects, they actually contest for bandwidth, of which has been shown to actually degrade the page load performance over non-prioritization schemes in practice. So WebGaze actually avoids these worst-case HTTP2 performances by utilizing a collective fixation threshold to only push objects of which are above the maximal importance to the user, a maximal importance to the user, and the specifics of the collective fixation threshold how it's calculated to actually determine this really high priority set of objects is discussed in the paper. So how do we actually implement such a system and test it in order to evaluate it in terms of uPLT? So we download the same 45 pages that we featured the uPLT studies as well as Gaze studies locally. We serve them from an HTTP 2 push enabled web server. And while we load the pages in using the methodologies that we discussed before, we take videos of the website's loads, similar to the uPLT study, and we host the videos again on crowdsourced platforms in order to obtain the resulting uPLT values. So in order to determine whether or not we improve the user experience relative to a few alternatives, we present two baselines as well as one state-of-the-art prioritization system that we compare to. The first is the default page load. So this represents the page just loading under standard HTTP 2 conditions. The push-all approach, where we identify all resources which are fetched over the network during the page load, and we push them with the initial HTML. This is to test server push at its extreme in terms of the user experience. And then there's Klotsky, of which was a system presented at NSDI 2 years ago, NSDI 15, of which actually uses a load time estimator to estimate the time of resources and pushes them with any resources that can be loaded within a given time budget. And the time budget is supposed to basically represent a user tolerance limit. So now let's give a short demo into how WebGaze does relative to the alternatives. It's only about a few seconds, so if you can pay attention, as the crowdsourced users were as well. So if we move clockwise, we see the default Klotsky push-all WebGaze alternatives. And hopefully you saw it, but WebGaze is already loaded. And we're still waiting on one more object. OK. That's the standard user experience on the web, right? So even if you didn't perceive a difference, hopefully you did. But if we move to the crowdsource results, WebGaze actually beat out the closest alternative, which was the state-of-the-art, by 2 seconds in terms of the median uPLT. And so in order to understand the intuition behind this, if we take a freeze frame of the load process at 6 seconds, we can see that the web objects corresponding to the regions of high collective fixation were indeed loaded first over the alternatives, which WebGaze is in the bottom right. So this was just one specific example of a site in our corpus, but how do we do in terms of all of the websites? What are our performance results in bulk? And so in order to understand this, we provide the following CDF percentage decrease in the user perceived page load time. So what we see here is that delivering objects that are important to the user does help in terms of user perceived performance in terms of this new metric that we generate. Specifically, we improve over the default by 17% at the median, 12% over the push-all approach at the median, and 9% over the state-of-the-art at the median. If we move to the 95th percentiles, we can see improvements up to 64% over the default. And if you'd like to see case-by-case studies, as well as comparisons to the traditional PLT metrics of which we mentioned at the beginning of the talk, these are also contained within the paper. So lastly, just some intuitions as to why we do better. So if we look, we see that uPLT improvements over the default are actually coming from just the general prioritization. So HTTP2 server push is able to not only achieve benefits in terms of the page load time, but the user perceived page load times. Improvements over push-all come from prioritizing the right set of objects, specifically only the objects that are relevant to the user in the above-the-fold content, as opposed to all of the objects that may be within the page. And finally, improvements over the Klotsky system over the state-of-the-art come from prioritizing the right set of ATF objects, not objects of which we've determined beforehand are actually important to the user, not just any of which can be loaded within a static time budget. So we have to mention that we do indeed have a small left tail for the results. And so we need to get some intuition as to why we do worse over the alternatives. Normally the cases in which we actually, the other cases outperform us, specifically between the push-all and Klotsky methods. And if we analyze our worst case performance over push-all, it's because pushing everything with HTTP2 server push actually sometimes works. So if the sites are small, lightweight, then we were observing that these sites would actually render quite instantaneously. So just optimizing a specific subset isn't enough. So it's basically we need to be less conservative in some cases as to what we identify. If we compare to Klotsky, Klotsky is actually thresholding, of which if an object is very large, it's actually preventing these worst case HTTP2 push performances via its load time estimator. So basically, we need to further analyze the trade-off between not just utilize the collective fixation as feedback, but measure either object load times or object sizes and incorporate this to a formal trade-off as future work. So where to with WebGaze? There's certainly more work to come. The first is, as mentioned, actually tackle the formal optimization problem between object load times or their sizes, as well as the collective fixation measure. The next is to actually utilize saliency modeling, of which is a well-studied aspect of automatically obtaining a collective amount of users' gaze on screen. And we can utilize this for automatic gaze feedback and automatic generation of collective fixation without the need for user studies. And then the last is WebGaze on mobile. This requires a new set of gaze hardware and tracking tools, of which is currently underway. So in conclusion, we've generated a new metric, of which is brought about by a need by traditional metrics not being related to the user quality of experience. We generate this metric with real user studies, and we optimize for this specifically by obtaining feedback in terms of user attention, utilizing the user's eye gaze, and creating a system of which formally optimizes, formally prioritizes regions corresponding to the objects of high collective fixation. All of these results, including the data itself, as well as the gaze tracks and the comparisons, are available on our site, www.cs.gaze.stonybrook.edu, which will be updated frequently with our future work. So stay tuned. Thanks. Oh, yeah, sure. Oh, you got it. Go ahead.
Hey, Sanjay from Purdue.
Yeah, hi.
I like the way you did gaze tracking. I have a comment and a question.
Sure, yeah.
My comment is the way you do push all is you're having objects pushed concurrently.
That's right.
We do have a system called Parcel that was published in Conext where we don't push concurrently but sort of schedule them carefully.
Yeah, so I know there's the mechanism in HTTP2, like a priority frames, in order to basically enable, in terms of maybe these objects are dependent on one another, you can only send, you would only send an object until its previous object is actually finished being delivered. So is that sort of...
Yeah, I can talk to you more offline on what Parcel does, but it does some careful scheduling of packets.
Okay, so it's like an intelligent push-all scheme.
Yeah,
Okay.
and the results are much better with that. But my question is, with this gaze tracking,
right?
Given that pages are so personalized, right? So different users might be seeing very different objects.
Yeah.
How does this work in that context?
So although what we've noticed is that for personalized pages such as Facebook and Google+, we've done some additional experiments, and we know that the regions of the page are actually relatively static, even though the actual content in the regions is pretty dynamic. So we can utilize, move to some dynamic URL matching in order to deliver like whatever object would be corresponding to that region of high gaze overlap, as opposed to just the object itself.
So in your experiments, the pages were different.
Yeah, there's some experiments in the paper about some specific sites like moving towards a fully content-specific WebGaze, where we analyze some sites and where the page itself, the structure is appearing similar, even though the actual content is relatively different.
Thanks.
So.
There's a lot of questions, so let's keep it short and then.
Oh, okay. Hi, Yimei from Tsinghua University, and you use eye gaze to capture the objects that are important to user experiences. So my question is, do you find any pattern? I mean, is there likely to be a object that is more likely to affect user experience? What kind of object?
Oh, in terms of everything, yeah, it seems to be pretty much banner images almost completely dominate overlap, and if you actually plot these against the existing saliency models, they're suggesting like similar things. So
there is a
pattern. The accuracy isn't there yet, which is why we're actually utilizing actual feedback of gaze tracks, but you could definitely see an overlap in that regard, and that these dominant banner images just attract total demand for attention. So any dependent objects of which are required to load those as soon as possible are very important to optimize.
Thank you.
Thank you.
Okay, I'm also from NetApp. So you use Gaze to improve the uPLT. So have you
correct.
thought about using Gaze to measure the uPLT as well?
Oh, so actually an automated uPLT measure that doesn't depend on user studies. Yeah, so we're actually working on that right now. We're trying to create like a sort of like a speed index metric, if you're familiar with it, that can be similarly approximated using gaze feedback. And then we could kind of systematically develop the whole thing, right, if we can automatically obtain gaze. So,
okay, I'll look forward to
that's the next step.
Shankar from AT&T Labs.
Hi.
I really appreciate the fact that you guys are looking at the visual aspects of user experience, but the user experience, important factor of user experience is also going to be the interactivity, right? Most web pages are going to be interactive, and some of these objects that you fetch may not be important visually, but have JavaScripts that might improve the interactivity, right? So I was wondering how your experiments, which right now are just videos being replayed, which captures the visual aspects, correlates with the interactivity experience that the user might have, and how does your prioritization work when you have such interactive web applications?
So that function is admittedly a next step. So we actually want to move from just having users view a visual medium, of which we've done some other user studies in terms of making it dynamic and content specific, but we haven't moved towards user actually interacting with the page. And but that would probably require a new metric other than just page load time in order to maybe a interaction time of when the user perceives that they can.
The DOM interactivity is sort of determined by the page load time, right? Which is one of the reasons why that has been used as the gold standard thus far. So I'm just curious how this correlates with that.
Okay, all right.
Last question.
Hi, Daniel from Kaiserslautern. I was wondering, do you have a sense of optimality? So how much further potential is there for improvement?
Yeah, that's a good question. And so I wish we did, in the fact that there would be, once there's more formal policies that come out for server push, of which basically define some optimum. Right now there's a general set of guidelines, but they're all just, Google has produced some. And they're all just general recommendations in order to, but they're also very conservative because they assume that you have no you have no actual domain knowledge of the page itself, other than just having access to specific objects. So I imagine optimality will be determined of which we'll actually compare to once these policies are actually fully determined in practice.
Okay, great. Let's end there. Thank you, Conor.
Okay, yeah, thanks a lot.
And